Oh, hi everybody. This is Joanne, and thank you for joining us today for another episode of Read Science. I'm joined by my co-host Jeff Schomeyer, and special guest today is Susan Kieffer, who is a emerita professor at the University of Illinois. And I've got an alarm going off. One second.
Hi folks, I'm glad to be here.
Yeah, live television.
Okay. All right, thank goodness this is a Google Hangout, and yeah, that's something really, I don't know, it's important, but okay, so let's start again. Our guest today is emerita professor from the University of Illinois, my alma mater, and also where I happen to teach. She is a planetary geologist and a recipient of the MacArthur Foundation Genius Grant, a member of the National Academy of Sciences, and she has a wonderful blog called Geology in Motion, and I definitely recommend you check that out because it takes current events in geology and puts them in perspective and explains a little bit of the science behind that. And that's what's happening in her book, The Dynamics of Disasters. I'm getting a little reflection there. And this book is like sort of a go-to guide for topics in geology for big disastrous events. Susan, welcome. Why don't you introduce yourself to the audience?
Okay. Hi folks, I'm really glad to be here today. I'm sitting in my home on Whidbey Island in the Pacific Northwest, up in kind of the treetops with the fog all around me.
That's great. Well, thank you. Welcome. And I'll let Jeff start with the first question.
Susan, it's great to be with you, and it was fun to have some physical science to read about all these earthquakes, tsunamis, volcanoes, wind, and things, and get some more understanding about where those all come from, what they do, and things. In tune with our big topic, which is always science communication, I wanted to say some thank you and start off with this quotation from page 49 of your book, where the first time you say, our post-field trip reflection introduces the issue of communicating with the public about what we know and don't know. And this is just after you've had a conversation about science and scientists and our relation with known knowns and unknown knowns and known unknowns and unknown unknowns. And the question then becomes, we have a lot of tricky concepts to communicate with the public, and I think we're going to be exploring that through this whole conversation about how to get across, how to choose nuanced topics that don't fit into quick sound bites and things. That's very nice. How do you approach this idea of communicating these large ideas about these disasters, and what you want people to end up knowing about disasters and the causes of these disasters as you were writing? Just an easy question to start off with. Yeah.
That was a long question. I think part of the challenge for me was learning the science and then thinking about how to communicate it. And so I had to learn much, much more than I put down, because until I really understood it myself, I couldn't figure out how to say it to the public. And even then, it was write and rewrite and rewrite. And I had not had experience with storytelling. Research scientists, you don't tell stories. You write pretty much according to a template. You introduce your problem. In a typical scientific paper, you introduce your problem. You have a background section where you review what's been done. Then you say what you did in the laboratory or the field or the theory. And then you talk about your conclusions and maybe your speculations. So it's really kind of a template of how you write a research paper. And writing about these events in a book form directed to a completely different audience was really a challenge. And I think the secret that I eventually learned was to try to pick out little pieces of the story that people could relate to and put those in, as kind of hooks to draw the people into the science.
It's a challenge for scientists and for the science writers, but I think everyone who writes now and reads from those is learning from how to do something that is akin to narrative, to make the book interesting and to bring in characters, in this case particular disasters and things, but also to explain as you go along, and to keep all those balls juggling in the air. Do you think, you've taught for a number of years, does teaching help you with that, communicating, learning how to communicate to people who don't understand things yet?
Oh, I think teaching definitely helps. I think writing this book would have made me a better teacher too.
Mm-hmm.
I just didn't get around to trying to write a book until very late in my career. But again, teaching, I found teaching Geology 101 to be incredibly challenging. And again, it's because you're covering a large variety of topics, and I don't teach well unless I really understand something well.
Mm-hmm.
And I think the good teachers really do have an amazing comprehension of what their subject is, and then a real talent for simplifying it.
Now that you're on the other side of this book, do you think that scientific meetings would improve if people would tell more stories as they were giving their papers?
I don't know, if you've got a 10-minute talk, you don't have time for a lot of stories.
No.
I think in geology, we're actually really lucky because we have a very visual subject, so we at least get to use pretty pictures sometimes, even though we're not telling stories.
So now we had a little bit of pre-discussion here, and you had commented that your editor at Norton, I love Norton. They've always got fantastic books, and I treat their authors well. At least so far is all I've ever heard. But your editor gave some feedback, like, okay, no histograms, no graphs, no, it's going to look too much like a textbook. How did you feel like you were being too textbooky, or so you're going from somewhere between a research paper to some flowing narrative and fanciful story. So you're somewhere in between, but you wanted to be more than a textbook. Yet you were cautioned.
I think the problem was I didn't think I was being too textbooky when he thought I was. So we went for a couple of years where the most common comment I got back from him was, "It's too textbooky." And we did have a funny go-around where I misunderstood what he meant by figures, and I thought that it meant I could include the occasional graph. And finally he said, "No, I mean photos." And so we have something like 70 photos in this. And I must say, if I was going to do another book, one of the things I would do early rather than late is make sure I have the photos lined up. Mm-hmm. Because getting the permissions in this day of legal issues, getting the permissions and finding really high resolution that they need for print ended up being a last-minute effort on our part to get everything just right in it. And so, I mean, it's actually amazing out there how many photos. You think you can go out on the web and grab a photo, which is easy to do for a blog or for a draft or a book. Mm-hmm. But to actually get that photo in the quality needed for a print book is another issue. And then if you start having to pay $50, $70, $150 a photo, that adds up.
Right. So as you said, you've got 75 or so photos. That's a good number of photos. So we've encountered this sort of thing with other science authors, is that they are cautioned, don't add a graph, don't add complex mathematical equations. Was there any temptation on you at all to add an equation here and there? Because that's the best way to describe something, but not everybody thinks like that, right?
Yeah.
I think I actually have one equation hidden in words in a parenthesis. It's just a little, I don't remember which one it is, but
yeah, an equation in words. Yeah, I noticed that.
Mass times acceleration or something like that. or kinetic energy. I think I was trying to explain energy and momentum in one case, and I put it in parenthetically. I think equations really do scare people. I still think that simple graphs probably don't scare them as much as we fear they do.
Mm-hmm.
And there's actually, I saw a really innovative math program somewhere. It's called something like Math Just in Time, and it's an effort to teach sort of remedial mathematics within an earth science course. And so the math is brought in as it's needed and as it's relevant. And
so you don't need a full suite of calculus and differential equations to be able to understand it.
Right, and this is more like introducing students who are afraid of graphs or interpolation, just trying to get it into a basic course. And it looked very successful. It's been running a couple of years.
That's really interesting. I've not heard of that course. I'll keep an eye out for it.
I think it's coming out of the CIRC program at Carleton College.
Okay.
Well, then do we need to ease in and start including a few more graphs with each new book? I have the feeling that even if people who haven't been schooled in it don't read graphs analytically or quantitatively, they can still see them qualitatively, and I think they get still a helpful picture of things increasing, things doing this or that, just the shapes and impressions from them that are still valuable, plus a bit of desensitizing, don't you think?
I think it could happen. I don't know how much leverage I'll have to try it in my next book. There's a wonderful series of science books. They're written. They're called the Cartoon Guides.
Yes.
And he does a remarkable job of introducing science in a way that's and hard concepts in a way that's very palatable. And I actually used one of those, Cartoon Guide to the Environment, when I taught sustainability. It just was students could really dive into it to get an introduction to an issue.
But talking about figures could also be numbers, and that's sort of we've been talking to a few people and cosmologists, people writing about cosmology. We've been discussing the idea of how to deal with exceedingly large numbers in the universe and how to deal with things like deep time. Deep time is an incomprehensible idea that keeps coming up in geology too. But in your case, it seemed like there was less deep time, but every new topic, every new thing, you've got tsunami waves, and they're huge, and they have huge amounts of water, and you've got the volume, and you've got high-speed material ejected from volcanic eruptions, and you've got enormous amounts of energy released in earthquakes, and you've got wind with incredible destructive power. And almost all of these things have numbers and quantities and magnitudes that are beyond comprehension. So, this is another one. What do you do? And I know what you did because I've read it, and I think that works at least as well as anyone else has been able to do. But it's a tough challenge, isn't it, to try to get some of these big numbers and big ideas across somehow.
Yeah, I was constantly thinking what would be a good reference for conveying the magnitude of this or that. One of the funny ones, or one I did, which a reviewer in Nature commented on, was I think I talked about a tsunami being higher than any mountain in Minnesota. And I actually had to go over, call up an atlas of all the states and see which state am I going to reference for this, I think it was 1,400-foot high tsunami. But, I mean, at least it stuck. It got noticed, and that's the whole point of it, is to give something. I have a number of cases where I talk about, 80-story buildings or so many football fields, just to try to bring across something relevant.
Like a sense of scale.
Yeah, I should say that I purposely didn't go into the biggest volcanic eruption known in all of geologic time. I tried to confine my time scales to hundreds to thousands of years because humans seem to lose track of time after the equivalent of a couple of generations of people.
Mm-hmm.
We care about things for our children. We care about things for our grandchildren. But beyond that, it's very hard to get us as a race to think ahead for longer times. To plan for centuries. It's just something that doesn't happen.
But then, from the way you were looking at these things, how important was the time? Because you were, you concentrated more on volcanic eruptions, for instance, on the size and the destructive power and how much could be ejected and where they come from. Not so important, really, to know exactly what year it was when Vesuvius destroyed Pompeii, where I was last week. And the largest historic eruptions ever, but the size is something that's always true, always has been, and always will be. And so time didn't seem to be quite so important a thing to hold on to as I was reading what you'd written.
Yeah, I think I put in as much detail as I could because I was trying to force myself to be accurate.
Mm-hmm.
But the other thing too is if I talked about an eruption, well, I mentioned the Toba eruption. I mentioned some things that happened on the 70,000 year or in one case tens of millions of year time scale. But it's important that the public doesn't get the concept that those might happen every day. I mean, maybe they happen once every 100,000 years, and maybe that'll be tomorrow, but it could also be 500,000 years from now.
I certainly want to come back to that later, but also it seemed like you were talking about you would choose recent storms, tsunamis, earthquakes, and things, almost with the idea that it is generational memory, and so they seemed more like living characters that people could relate to rather than distant, never have to worry about those sorts of things. They seem more present that way.
Well, it took me 3 years to write this book, and at one point I was just saying, I hope for the sake of humanity as well as my book that nothing major happens until I finish do another revision.
Right, so because the tsunami chapter has got the Sumatran and the Tohoku, earthquake tsunami. So as I was reading that, I was like, yeah, this is valuable, and knowing the time frame of book writing, I was like, that's amazing. You got this all in there.
I think I got Sandy in there, but that was about the last one. There were some tornadoes. Norman, Oklahoma tornado we couldn't make that revision because the book pretty much gets locked in 6, 8, 10 months before it actually comes out.
But even the Joplin tornado still seems recent to me, and you talked about that.
Yeah, the Joplin story was just amazing, and that was one of the places where I first started thinking about and time ideas. The Time Online Ideas section picked up on these chain reactions, where I commented that not all of the people who were injured and died were injured by flying debris. That there was actually this second effect, that the debris had dirt on it, and these people got a fungal infection from the dirt on the flying debris.
I have here a note to ask you about the startling fact about these odd cases of Zygoomycosis and where that came from, and I wanted you to tell that story again a little bit because it was so, well, this chain reaction idea is quite so that there are these things that extend out from the direct consequences of the disaster that we don't think about, and here's something that killed 4 or 5 of the people and is related to the wind. But what an odd and say it again, startling indirect sort of effect.
Well, it was. I mean, one of the things I really, really enjoyed about writing a book like this compared to writing a research paper was just the unexpected things I learned. And when I came across that, I don't remember the exact process of how my brain worked on that, but when I came across that, it was, wow, I never thought of this. And clearly the medical people had problems. My memory is that it was a mystery for a while. What was going on with these ill people? And I think in a larger sense, the whole event with the earthquake off of northern Japan in 2011, and then the tsunami, and then the Fukushima Daiichi power plant, and then effects cascading into the Japanese and global economy. It's just the main event was the earthquake, but all these other things followed, and we don't do a very good job of anticipating these.
Hmm.
And that when you think of things like cholera in Haiti afterwards and famine, you know, that kills so many people after a volcanic eruption, because of, you know, the ash or, you know, the multiple things that occur after a volcano eruption that leads to starvation. And, you know, for people, it's not just that they're in the direct line of, you know, the pyroclastic blast or the, you know, very hot flow or the poisonous gases. It's a secondary event.
Right.
Or events.
Well, and these are still, even though we have, you know, a number of them all the time, they're still, in some sense, rare enough that we don't have example after example after example to drive home all of these chain reaction events that can happen and all of the consequences that follow on these. Startling. And I'm thinking about the big numbers again, and just reading the sheer numbers of people who have been killed year after year by these things is amazing. Tens of thousands, hundreds of thousands by events. These are such startling big numbers. And I was, you know, trying to understand when a volcano explodes and the enormous volume, you know, square miles, cubic miles of material ejected and thrown out. It's like,
well, yeah,
it's so huge.
right. And the truly big eruptions that I really don't talk about, the really, really rare ones where it's hundreds of cubic kilometers or cubic miles of ejecta, I mean, those are really civilization-ending events. And the problem, if you write and focus on those, they're kind of like the Hollywood fodder, and it takes away from the attention to the things that are actually more likely to affect us.
Yeah.
We know that on the time scale of decades to centuries, big enough events are going to happen that we need to pay attention to. And so let's not, and the point of this book was to focus on those and not have the distraction of the truly big events. I talk about one big landslide, right. Talk about one big volcanic eruption that we think probably affected, I mean, reduced the population of humans to such a small number that it affected really the whole genetic evolution of our species.
Yeah, so that we had an evolutionary bottleneck there to get through. Then, and so, yeah, you can do some of those for examples, but that brings up, and you'd mentioned it, the ideas of trying to get across the idea of reasonable risk assessment too. Are there more smaller events? How much risk is there of that happening? How much risk is there of a big thing? And then we've learned in recent years, people have been thinking about that humans, at least what we get from our newspapers and things, we're not very good at relative risk assessment about whether we're more likely to die from exploding volcanoes or terrorist foot bombs or something. And so you are balancing all of this, right, and try to keep a better sense of balance about where the risks actually come from.
Well, I try to point out the geologic things we need to think about, but it's also very clear to me that it's way beyond the role of a geologist to say how society should deal with those. It's really a problem for all of society. It's for the insurance industry, the political leaders, the emergency responders, and I actually conclude the book with a discussion about the needs in society for basically many, many different talents to be brought to the problem of how we exist when nature's going to throw these hazards at us. And I mean, our traditional mechanism, a primary mechanism, has been the insurance industry. And right now, the global insurance industry has just been reeling. Because there were so many disasters in the first part of this century, particularly, that it's the system's overloaded. But I haven't followed how they're making changes. One of the problems is that these fairly rare, not the truly rare, but these fairly rare once per century, once per 1,000-year events have very high consequences. But you can't use statistics to incorporate them in to the insurance models. So some of the more progressive insurance companies actually are using the science underlying these to try to understand then how to do the insurance policy and the financing.
How long does it take to? Are we fighting a battle of having to try to get across these sort of nuanced ideas? You know, the idea that big events may happen here and it's once per 10,000 years, but that doesn't mean it's 10,000 years between each one. Even simple ideas like that, when we are, you know, being driven by news outlets or policymakers who seem to react only to sensationalism or to crises or to something, and there seems to be so much of that sort of noise that it's very hard to get across more than a soundbite. Another useful reason to have your book for people to refer to and read and get that background information. But does it seem like an uphill battle trying to discuss any of these ideas with any sort of sophistication?
I think I'm not a good soundbite person. I'm a classic academic that gives a long answer, as you could probably see. And fortunately, we have some people who are very good with sound bites. But yeah, the whole concept of communicating probabilities to the general public, which it's very difficult. And one of the communities that does it the best is the earthquake community, because and I've been particularly impressed with what I've learned in the course of writing the book about how California communicates the earthquake hazards there. And one of their techniques is constant exposure of the earthquake ideas to the public and the probabilities of earthquakes. And so I think that is really a model for how we need to look at some of these. But you know, trying to, oops, sorry, I just kicked my desk. Trying to discuss and convince the general public that, yeah, there's a 1 in 1,000 chance that this could happen this year, but it could happen this year and next year as well. And there are a number of cases where the 100-year flood has occurred 2 or 3 years in a row in places, and it's taken out a couple of dams under construction. Was one of the examples I looked at.
Is this something we could talk about in terms of science literacy? And when I say that, I'm thinking of making science part of a general cultural phenomenon rather than something just done by scientists and just of interest to scientists. So when Joanne and I work on science literacy, we're usually thinking of science as part of an everyday culture sort of thing. And to me, that sounds like what you're describing about California's approach to earthquake literacy, if you want, and understanding those things.
It is. I had an interesting experience trying to make science relevant. I used a good fraction of my MacArthur fellowship money to work on teaching science to homeless and at-risk junior high school kids in the Phoenix area. That's about 20 years ago. And these were students who had very limited math and reading skills. And so the question was, how do you make science relevant to these kids and get them interested in it? And what we ended up doing was just taking whatever happened of interest that day and turning it into a science lesson. So maybe they'd be out playing basketball and it would rain, and they'd bounce the ball through a puddle, and we would turn that into a lesson on meteorite impacts and perpendicular impacts versus oblique impacts. And one of the most successful lessons I had was I was driving down a highway, and I carry a fire extinguisher in my car.
Right.
And the person who was with me set their briefcase down on top of the fire extinguisher, and it detonated inside the car going 60 miles an hour. And it turned out those homeless and at-risk kids knew more things to do with fire extinguishers than you or I as a could imagine. And we got talking about the chemistry of fire extinguishers, and it turned into a chemistry lesson.
And so, and here you were trying to tell us that you weren't much of a storyteller, but it sounds like you found the value of telling stories with these kids.
We did, and I had the fortune to be working with a professional teacher who had skills that I didn't and could really help me with the relationships with the students. And so that was another case where I learned a lot about teaching in a way that I hadn't expected. But it's a little bit what I try to do in my blog. There's just science around us everywhere.
Yeah. Well, that's what I was going to say. Congratulations on your work with these kids. It's definitely something I get behind. But that's exactly what I felt like in this book. It was definitely, I mean, there is no way you could, if you sat down and read this book, that you would not walk away knowing some more physics, unless you're already a physics pro, you know, and even some chemistry. And that this really shows through. And I'm just looking at, you know, I just want to emphasize that, you know, we get a lot of authors on here, and very few of them are actually scientists in the field, in the lab. You know, we get a lot of science writers. They're fascinated with science. They learn a lot. But it's nice to have, you know, a scientist who's done work in the field to then tackle, to say, okay, I can't explain this the way I would to my colleagues. I'm going to explain to the general public. And it's you just done such a good job, like just teaching some basic physics through current events, through things that you know, most of us are fascinated by, if not impacted by. But you know, when I introduced you, I didn't read your interests. So I've got here your research interests include geological physics, nonlinear processes, and nonlinear data analysis. Stability and sustainability, and I want to ask about that. And you are interested in planetary sciences, geological fluid dynamics, including geothermal, epithermal, and volcanic environments. And the list goes on and on. So I'm interested in this, that you are a planetary geologist. But to be a planetary geologist, you sort of have to know the Earth. But so this is obviously earthbound, right? You talk about potential landslides on Mars or something like that, so that we think that sort of happened at some point. But you're talking about earthbound events, but, you know, here I've seen most things referring to you as a planetary geologist. So how does this apply to looking out to the other worlds?
Well, when I wanted to be an astronaut from junior high school on, and that didn't work out. But I started grad school just about the time that planetary sciences was really emerging as a field. And I went to Caltech, and their planetary program was in the geology department. And the whole philosophy was to apply geological rather than, well, I'd say rather than, but to apply, I'll say that and then qualify it, to apply geological rather than astronomical techniques to studying the moon and the planets. We actually use both astronomical and geologic tools, but the basic principles of how we study the Earth have been applied to the planets since about the early 1960s. And so they took a bunch of physics, math, and chemistry majors my year into the graduate program at Caltech, and they said, audit Geology 101 and spend a few weekends out in the field so that you guys know that rocks exist, and then go ahead and do whatever you want. And I just fell in love with the geology part of it. So I bounced back and forth between studying processes on the Earth and processes on other planets and satellites. And it's just been a really exciting time to be a planetary scientist, and particularly a volcanologist. I started studying Old Faithful Geyser as an analog to volcanic eruptions because I'd never had much geology, I'd never had petrology, I hadn't had crystallography. I couldn't become a standard volcanologist. So I started studying Old Faithful Geyser in 1966, thinking I would spend some years learning how that geyser worked and then gradually move on to volcanology. Well, 3 years later, they discovered geyser and volcano eruptions on Io, a satellite of Saturn. a satellite of Jupiter, get my solar. And the next year, 1980, Mount St. Helens erupted, and then things just kept happening, either on Earth or on the solar system for decades. And it's just been a wonderful time to be on the in that field.
It's so I mean it's so interesting how they're tied together. I've got a couple questions that are in from viewers, so if that's okay, if you are able to address them. So we've got this first one that says, fascinating point about global insurance. Are there any, and if you know this at all, are there any reputable organizations that monitor the expenditure versus the income of insurance on a global scale? Now, this sounds like it's beyond your reach, but maybe you know.
That is, I'm sorry, viewer, that's a great question, but it's, you might look up, the one insurance company I know that's been doing it for a long time is called Swiss Re, and they have quite an informative website. I don't know if that would be any help, but I know that's one that we commonly cite as using the best science that they can get hold of.
Do you have any more insights? Do you have any more insights to share about how they use scientific ideas? Presume, there's probably an actuarial aspect, I suppose, but do they do more than that? How are they using ideas from science to get a better handle on their work, on their business?
My information is secondhand from colleagues who have worked with them, and I get the feeling that they are really interested in the details of the research scientists at the forefront. If you have a model of volcanic eruptions, what's that model about? How does it work? But I don't actually know. I've not been inside the insurance industry.
Okay. So here's an odd question, I think. What was your favorite chapter to write? What your favorite topic? Like you felt like you really had a handle on it, and you were expressing things the way you wanted. The one that made you really excited to be sharing this topic.
I have to look at the table of contents. There was one chapter I wrote in 3 days, and I thought, oh, this book's going to be easy. I think it was an early earthquake one or something. I think in some ways maybe the landslide chapter, the one that's called The Flying Carpet of Elm. And
about how in the world landslides can move so fast.
Right.
And the mechanisms for that.
But also that's the one where I say landslides are like teenagers.
Yeah.
They're all different.
They're all different. And this was the one where you give an account of you falling down. Like
jumping off the roof of my house to try to escape my parents. I was trying to sneak out of the house, and I jumped off a second-story roof and sort of forgot that my feet would land before my chin, and my chin ran into my knee and probably came close to breaking my neck.
Yeah.
And I brought that in because there was a landslide in Switzerland where there's an eyewitness sketch, and the rocks bounce off a cliff on the mountain in a way that I related to my chin bouncing off my knee.
That's what I liked about the book, was I felt like there were enough relatable things, either from your life, and whether it was your husband overinflating a bicycle tire, sort of underestimating his strength there, and explaining, the gas law, PV equals nRT, which you didn't say that law. You didn't say that. I said,
equations.
I know some equations, but you explained that equation very clearly using that demonstration. And you would even use little things like, again, you're saying the sense of scale. Like you'll say, well, so the amount in a volcano is about this, whereas the amount of gas, in a can of Coke is this, so that people get this idea of, scale, the relatability, and that is, to me, what I found most charming about this book. I felt like people are going to walk away knowing science. They're going to walk away having a sense of scale. They're going to walk away seeing how this is relevant, and even a little bit of a sense of how common these things are and how devastating they could possibly be, as well as think about future scenarios that could be helpful. And in a way, I thought, you were talking about, it's not the geologist to be able to solve, the problems of how do we, tend to the subsequent crises. It's up to the politicians. It's up to, probably healthcare workers and things like that. So in a way, this book could be quite informative, sort of like there's that book, Physics for Future Presidents. This could be like the, geology of disasters for future presidents, or, and all politicians.
I'd like to characterize those, which I think are important too, as making connections from the scientific ideas to things that are outside science. And I think that enhances what I refer to as the scienticity, but that makes more connections for people to do. That makes more literary allusions almost, which enhances, makes things more interesting and easier to hold on to and to comprehend in the end, I think.
Well, thank you very much. I appreciate that. I actually, I started my blog about 4 years ago, I think now, and I went through a phase where I decided to see if I could go for 2 weeks and find something to post about every day related to geology and motion. And it's a fairly specific field. I like to look at things in geology that move and preferably move fast.
Yeah.
And I admit I was living in Urbana, where Joanne is, and using the local newspaper and trying to, and I use the web too, but occasionally I would stretch things to try to get some science into the blog, but it's there. I mean, it's really amazing. Some days it hits us in the face how relevant the science is, and other times it's a little more subtle, but it's there.
Some people complain, and this is something I remember I bring up over and over again, a footnote in the Feynman lectures where Feynman strikes out against the people who think that scientists are cold and insensitive and we've taken all the mystery out of the world, and he takes a brief footnote to say, excuse me, but I think I see more if I see all the mystery that you see, but I know about fusion and why stars are bright and how they are and how many there are. And I had that sort of reaction when I was reading this morning the chapter about circulation and thermal convection in the air. And I could start to picture the air things and where the clouds were coming from and where fronts were coming from and how cyclones and vortices might turn into destructive storms. And I like the feeling, and I think I got that. And I think that's a valuable thing, to look at the sky and see the storms. Clouds can be beautiful, but how interesting it is to know that they come about because of these large-scale circulations, thermal gradients, and Coriolis forces. I don't think that takes anything away from anything.
Those were hard chapters for me to write, too, because I had no atmospheric science training. I know for many, many decades I've had a frustrated desire to be a meteorologist. So it was fun to do that, but it was hard.
Mm-hmm.
And that's where you go to a textbook to learn things, but then how do you bring it back and not have it be textbooky?
Well, and maybe it's because it had a certain spontaneity and freshness, perhaps because you were learning it new and had a fresh perspective on it. But I got a very vibrant picture out of that, and I like now. Like I wanted to run out and look at the sky and see what the clouds were doing.
I love clouds. They're really great. It's funny. I've been sitting here, and one of the things I always thought was, you get up in the morning and it's foggy. But this is the Pacific Northwest, to remind the viewers. As I've been sitting here, and it's now 10:45, the fog has been coming in more and more and more. Like it's creeping in. And I have to say, I don't understand why that happens. It's something I'll have to go out and look up. But it's great fun to have an excuse to go learn things like that. Like, why doesn't fog go away in the late morning?
Well, it's the fun of being a scientist, don't you think? Well, it's like, oh, great, something new I can learn about.
Yeah.
So now you alluded to, whether seriously or not, the possibility of another book? Is this something you're thinking?
I'm still in recovery mode. It's only been out, I think, 2 weeks. Came out October.
Right. Yes, yes. It is very new. It is very new. But like I said, you alluded, and I thought, maybe she has an idea that's, you know.
I think once, maybe it's a compulsion. Once you write a book, you can't help but thinking, is there another one in me? And I think, I mean, I went through a horrendous writer's block. And that's one reason that I really have enjoyed my blog. In fact, I think probably I started the blog when I was still working on the outline for the book. It took me a year to get an outline that my editor would approve. And I found I could write more freely in the blog because I wasn't in this big structure of the book, and I wasn't going to be edited and reviewed and everything.
Yeah.
And so there's always been that question of, is there even one book in me, let alone more than one?
Right. I do have another question from someone in the audience. Is how closely did you work, or have you worked at all, with rescue workers to gather information on recent events? Are points in the book expressed not only on data, but how to best mitigate these events?
I'm not sure if that's one or two questions.
It sounds like two. It sounds like two. Let's start with the one. Did you work with rescue workers to gather information on recent events?
No, I didn't. In fact, my experience in Mount St. Helens, which certainly isn't recent, it's 1980, was that rescue is the primary goal for times during and after these events, and that the science is second. I mean, you really have to sit back and let the rescue operations go as the first priority. I've been around rescue situation. I didn't write in the book about work I did on big waves in the Grand Canyon in 1983, but there again, there was a situation on the Grand Canyon where there was very, very big discharges through Glen Canyon Dam, and there were rafting accidents. And the first priority was ensuring the safety of people on the river and working there, and then secondarily, the science data gathering comes in. I forget what the second question was.
It was, so are there points in the book expressed not only on data, but how to best mitigate these events? So do you approach the rescue efforts, or to minimize chain reactions, for instance?
Yeah, the last chapter of the book is, well, there's these little sections at the end of each chapter called reflections, where I meditate briefly on issues relevant to the chapter or peripheral to the chapter, and then try to bring them together at the end of the book. And I give some specific suggestions that individuals can do, like contacting their state geological surveys or the U.S. Geological Survey, looking at recommendations that the local emergency responders have put out about how to prepare. You know, if you're in a fire district, cut the trees back away from your house, for example. And then I talk a little bit about a vision for a global community that interacts more tightly on disaster preparation, mitigation than I think we do now.
While you're near that, I have two more things I want to be sure. Not big things, but I have another quotation from page 191 here, where, well, this is, I like these, and they're things that stood out for me, but you say, with weather patterns changing in response to climate change, free access to the best data, meteorological and climate data from all areas of the world is essential to maintaining progress and understanding the complex ocean atmospheric processes that are a continual threat to transatlantic shipping. And so you were talking about those specific things about rogue waves and related topics, but surely this applies in a much bigger way to all of these other destructive phenomena, and relate to your idea for a global clearinghouse, that we need to have more access. We don't need to keep cutting stuff back, and we have enough politicians who seem to think that collecting a network of data in the ocean is extra credit and isn't really serving any useful purpose. So here's your chance to say how wrong that is. We need that, and we need a lot of it, and we need free access to it to develop these pictures.
There was that was a point with a particular history, and that is that there has been a movement for recovery of expenses and or privatization of data going on for 10 or 20 years, and it has gotten to the point where it's impossible for some researchers to afford to get the data they need to do more research. And I think that's a very frightening thing for improving our research and our understanding of these phenomena. There have been bodies set up by the National Research Council to look at these issues. But again, it's a need for a global thing, because the Europeans can do one thing and the US can do another thing. And unless we're talking to each other, we're really not optimizing the way we could be handling our data. And it becomes, I think it came to the head initially in the meteorological community because of the global nature of weather.
Right.
But I think it's a trend that scientists are very concerned about.
When you were talking about, this is my last little written note, but when you were talking about early on about earthquakes and this phenomenon of liquefaction, where the earth, because of the way it's shaken and granular flows and such things, its nature changes and it becomes very liquid. You were talking specifically about videos from the 2011 Tohoku earthquake appearing on YouTube. And so I'm interested in how the ideas of social media might be used to increase some of this access to data, to get more information to the public, to present these videos where in a few, in 10 seconds you can look and see something that would be very hard to get into people's heads otherwise through other channels. It seems like there could be a lot of potential there.
Oh, I think there is. And again, the issue could be copyright. There were a lot of videos and images that came up fairly soon after the Tohoku earthquake, which have now been taken down. I haven't gone back. It would be actually an interesting exercise for me to go back and look if all of the videos I reference in my book are still accessible a year later on the web, because I think in some cases, in a number of cases, the very best ones have been obtained by commercial television or movies.
Oh, yeah, sure.
They disappeared due to copyright issues.
Right.
Yeah. They said, yeah, let's take this for our news program, and now it's, they paid the videographer, and it's,
And I know that's happened in a number of cases on the Tohoku earthquake tsunami videos, because we had a whole bunch of them. That happened actually a year I was teaching geological fluid mechanics. And it happened like the 6 weeks into the semester, so we actually turned the class into a research project. It was a very small class, and did a research project on the tsunami, trying to map out where it had hit. This was in the early days. And a year later, we couldn't find most of those videos.
And I know they used a lot of the videos from that meteor that came down in Russia. And, they use those to sort of go, which direction did it arrive and where, so to help them pinpoint where it landed. I see we're winding down, and I did want to make sure to touch on the topic of one of your interests, which is about global sustainability and how understanding geology can help. How does that even help us create a more sustainable planet?
Well, I think the geologic fact is that we're a planet with finite resources. And by understanding those resources and their availability, how we can recycle them, which ones we can use, not use, I think can really make us realistic about our sustainability goals. How many people can the planet support at a reasonable quality of life? We don't have another planet Earth to go to. And I did an exercise with one of my students, well, with one of my classes, where the students calculated how many planet Earths it would take to sustain their lifestyle. And students' lifestyles are fairly humble. But it turned out in most cases it was more than one planet Earth.
Mm-hmm.
And one of the young students' parents, she did the exercise for a parent because they had to do it for several different lifestyles. And it would have taken 12 planet Earths to support them. So I think that we live here, as Will Durant said, by geologic consent.
Yeah.
Mm-hmm.
And we need to be very respectful about that and think about our own use of the resources and the resources for future generations.
Mm-hmm.
That's good. You have been perfectly a wonderful guest, Susan. I appreciate a scientist's perspective and you working so hard to make a book that's not like a textbook. It's not like a textbook, people.
Thank you. I will send it to my editor.
I'll send a note to Norton. It's not like a textbook. It's very nice. Yeah, I really enjoyed it, and like I said, a book where I feel like, oh, good, well, for me, a refresher. It's a refresher on physics, but for some people, it might be the first time that they grasp that concept.
Mm-hmm.
And so I really hope, and then it provides so much information about recent disasters, and I just feel like it's a valuable book. So I really hope people will pick up a copy. And I had a few people on Twitter say, they couldn't join the event, but they actually ordered the book. So,
Good.
So,
I will send this definitely to my publisher. They'll be so glad to hear. Thank you very kindly.
I hope the publicists are listening who have sent us the books, so they know that we can still receive books and prove a valuable service here. It's true, Susan. I thought the using these ideas and giving the insights into the disasters, but also understanding where they come from and getting ideas about risks in a leisurely enough way that people could absorb the ideas is really a valuable thing and not textbooky.
Success. Thank you.
Is there anything we've forgotten to ask you? This is one of our favorite questions. Like your turn. It's free form. If you have anything that we just never got around to asking.
No, I think we've covered a lot. If the viewers have stayed with you for the full hour, I think I appreciate them too.
All right. Well, thank you, Susan, and as always, thank you, Jeff, and thank you to our viewers and the people who submitted questions. And we'll see you again next time on Read Science. And currently, we are slated to interview Chris Hadfield on November 14th. That's Commander Chris Hadfield from the International Space Station for his book, An Astronaut's Guide to Life on Earth. So I hope you'll tune in for that. And be sure to go out and pick up a copy of The Dynamics of Disaster by Susan Kieffer, Dr. Susan Kieffer. All right. Thank you, everybody.
Thanks, Susan. Bye-bye.
Bye-bye.